Greetings, friends. I'm looking at this, which is an example of one would call a technical joke via Peter. It's a quick and dirty power supply. A 30-minute job of a power supply. And I'm looking at this joke and it reminds me of something I did very similar to this joke about 15 years ago. 20 years ago when I was working at Intel. Okay. At the time when I was working at Intel, the major product that I was working on at the time was 88EC196, which is basically was made for Bosch, an automotive chip. Okay, it's an automotive chip with 256K flash, designed around the time of 1995. Okay, this chip, or I would call it this die, as it, when I saw them, they were dies, not chips. It had a CAN bus. At that point in time, the CAN bus was relatively new, and it was decided that the tester hardware, or the VLSI tester, or the programming hardware that we were using, was unable to make a realistically test the CAN bus with differential CAN high and CAN low values. So it was decided to create a test jig using this chip externally, and this chip would be used to create CAN signals, and we would be able to therefore be functionally test the CAN bus instead of pseudo functionally testing the CAN bus. So I was approached by two people, one Effie and one Ran Kafri, to create a power supply for this and to create a programming jig. The programming jig was RS-232, and they told me they wanted a full RS-232 with plus and minus 12 volt rails. And they said I'd have about a few days to design it. And they said, we're giving you a 16 volt net notebook power supply, which we have on the table. And we want you to create a programming jig. Came to me and said, you know what is it? Let's bona selam jester. Let's see how quickly I can do it. Okay. So how did I do it? I said, listen, you know what, they've given me a 16 volt power supply, and plus minus volts, it's plus minus 8. Not exactly, but no one plus minus 12. Boost it, nah, not going to do that. So what did I do? I took the 16 volt power supply. I took it through a couple of bridge rectifiers. I went out and found a couple of bridge rectifiers, a couple of 1N004s, to bring down the 16 volts to roughly 12 volts. On the 12 volt rail, I poked 7805. 7805, 12 volts to 5 volts. This took me about best part of 15 minutes. Went out to in Jerusalem, the local electronics store, and picked up some DIP no SMD business. Yeah, we're talking about a dip. Talking about some dip Max 232 chips. Max 232 chips. 5 minutes later, I had Max 232 chips and a few capacitors. A few capacitors in hand on a prototype board. I soldered everything up, did a loop back so that I could see that my Max 232 was working. I could TX and RX, and within roughly an hour, I went back to run Kafri, and I went back to Effie, and I put it down on the desk and said, "Yeah, it works." They looked at me and they were in shock. I said, "What have you done?" I said, "They expected me to go and boost the voltage and do things. Just went out and within an hour or two gave them it back working." They programmed about 30, 40 chips like this, and it was put away in some drawer, never to see the light of day again. Okay, it's an example of a quick and dirty design which I did, very similar to the joke done via Peter. Okay, I decided to take this one step further, and I decided let's go and show the chip that I did it for. The K32 chip, which was 88EC196, which was a flash variant of the 196. Flash variant of 196, which was only automotive part. Okay, so we've come to Intel 960, and I'm looking down on the architecture, and I find a chip which is something which I actually couldn't find the chip I was looking for, but I found another chip which is somewhat interesting. Okay, I'm going to talk about the 1896 960 MX. The 189060 was never released to non-military market. It was never released to a non-military market, and it was the biggest chip in physical die size ever to be made at Intel Fab 8. Okay, so here we have it over here. Okay, if we go down to the bottom, we're going to look at the die. This is a photograph of the 8960 MX, and we're going to take a look. I'm going to zoom in even further. Before I zoom in, you have 64 pins on each side. How do I know it is 64 pins on each side? I remember that it took up the full complement of the tester. The highest number of pins being able to be tested on the platform I worked on was 256 pins. And this was exactly used, full 256 pins, a full complement of the tester. Okay, we're going to zoom in. Okay, I've zoomed in to a bottom corner. Now, I worked 13 years at Intel doing wafer sort. Outside of Intel, outside of semiconductor manufacturing, they would ask, what did you do? And the term is BADAS, Bdikat Sofiot. What is Bdikat Sofiot? Generally, it's switching on and running through some tests. This is somewhat different, and I will explain some of the issues involved with wafer test. We're going back, once again, I'm talking about wafer test 20 years back. Technology of 20 years back, not today's technology. Okay, one can see, if one looks at these pads, that these pads have got a mark in the middle. The mark in the middle is what's known as a probe mark. So what has happened, I'm now showing you here. You have a bed of nails and you have your wafer. Your wafer is lifted to the bed of nails so that your bed of nails touches the wafer and is then checked. I was involved in the testing hardware, keeping it running, and test programs to understand why this tester tested this way, the next tester had a lower yield. It was all what I did for many years. Okay, so I'm now going to show you how one can test, see if this wafer was tested in a good way or a bad way. Okay, first check. Are the pins in the middle of the pad? Are the pins in the middle of the pad? Yes. We're going to go to the furthest pin on the left. It's in the middle of the pad. And if I go to the furthest pin on the right, it's also in the middle of the pad, slightly lower. Slightly lower, not seriously lower, but we're having a very slight angular movement of the probe card. The probe card is slightly slanted down. Okay, not serious. If one can see that if I take all these pins on this side, they are slightly lower in the pad. And these ones are slightly more central. There is a very, very slight wafer probe card theta. Very, very slight, very difficult to see, and not something which is going to affect the probing. Okay, so we've seen that more or less our angular setup of the probe card was good job. Okay, so we've now looked to see whether the angular movement of the probe card created a problem, but didn't. I'm now going to look to see whether the alignment of the pins in the Z axis, which is up and down, if that was correct. Okay, if that would be incorrect, what would I see? I'd see different size probe marks from left to right. I can see that probe mark is roughly the same size as this probe mark, Okay, all my probe possibly this one is slightly bigger. All my probe marks are the same size. What does that mean to me? That means to me that when the automation measured leakage and it lifted up the wafer to the probing height, it did it in a good way, as there was very good planarity between first pin and last pin in probing. Okay, shall we say good job? Okay. This is a good job. Okay. So now, once we've checked that, the next check that we're going to do together is we're going to check the pin alignment. So now, if we're going to look at a pin alignment, imagine you have a camera looking up at the pins from the bottom. If you're looking up at the pins, the way you look at my hand, you might find one pin going up, one pin going down. So that would cause these pins to be aligned left and right. We can see these pins are perfectly centered. These pins are perfectly centered. These pins are perfectly centered. 100%. Good job. Okay. So that means we've checked alignment. We've checked the Z alignment by the height of by the size of the pins, and we've checked the XY alignment. And we've also checked that we don't have probe card theta, which means the probe card is swiveled. So as far as out of 100% marks, this particular die was very, very well probed. Okay. As this die was never in use outside of military use, it doesn't surprise me. It means that you didn't have 10,000 or 100,000 or 200,000 touchdowns on this product. This was a very, very low volume product, and if you did one lot and the lot was 800 touchdowns on the wafer, your probe card is never ever going to get to the state where it's going to go out of alignment or being fixed. Okay, this is this die. We've looked together at some of the parameters of wafer probing as was prevalent when I was doing wafer sort. I'm saying it's no longer that prevalent. Why? Because at some point in time, the technology changed, and the technology changed to, instead of having bare wafers, there were CF balls on the pads, which means that you are not probing the actual wafer, but you're probing above the wafer. This had an effect on, this was done after I never worked on CF or C4. I'm not sure what the technology is called, but there were actually balls of, it's difficult to call it solder, but on top of these pads. Okay, on top of these pads were afterwards. This is talking about, okay. Why was it so important to have the probing in the middle of the pad for two reasons. One, if you probe towards the side, more than likely you're going to have more contact resistance. More contact resistance, and you have a more likelihood of breaking the passivation layer. Now, what does it mean, the passivation layer? That is the glass layer that covers your die. It's your top layer. Now, if you were to probe incorrectly the die and break the passivation layer, you would open the die up to degradation via moisture over time. So it would work perfectly at Fab 8, but somewhere down the line you'd get corrosion. Okay. So we're talking about corrosion. This is, okay. Urban legend related to this chip. It was an urban legend around this particular chip. This chip was only done for United States military. Okay, I remember roughly about 20 or 30 dies per wafer, P648, if I remember correctly. I'm going back 12 years to the last wafers, and when they were done in volume, very, very rarely did you want to see this product. Okay. The Lockheed Martin F-22. It was rumored that this chip was the chip that ran the Lockheed Martin F-22. Roughly if it was produced in 1996 to 2011, it's very likely that if there was one chip which was made, for this chip, that would be this Lockheed Martin chip. It was a rumor that this chip was used for the F-22, the MX960. Whether it is true or it was just an urban legend, I've got no way of knowing. What makes me suspect that it's not exactly 100% true is because 195 chips were made. 195 Lockheed Martin F-22s were made. If we're talking about roughly 30 chips per wafer, ballpark figure, one lot would have given you over 150 to 200 chips. So somehow the urban legend doesn't exactly hold water that the F-22 was designed around the MX960, even though as far as time frame concerned, it fits. Okay. We were looking at this MX950. Okay. So I've shown basically what was set up. The X, your XY, And your wafer probe, the bottom prober was a 6-inch Electroglass 2010. The top one was the LTX Trillium Multi Trillium tester. That's what I worked on for 13 years. Okay, if we're going to go back, okay, this is what I used to do for 13 years. Okay, what was my part in this? The operators would set up, would do setups. I also would do setups of products, and whenever the yield began dropping, or they were complaining that something was not working correctly, above the noise of the machines, you would hear the screech, "Ah, yeah!" And the operator wouldn't have given me a beeper. They wouldn't have called me on the phone. They would just scream and say, "Your tester is a tester shacham zayef. Your equipment is not giving high enough yield." I took a wafer, I ran it here, it gave me 100 dies less yield, and I took this wafer, I suspected it, I took it to the next site tester, and your tester is causing me problems. Naletapel was what a friend of mine used to say to me, "Do the necessary." And I used to ask, and whenever he'd say to me, "Do the necessary," I would always reply back the joke, "What is necessary?" Okay, so I was involved in the smooth running of production of this product and another 120 other products which were on Fab 8. Okay, we're going to look at some other dies. This is also another die. It's more difficult to see the probe marks because these parts have been, this die has been wire bound. I would sit many hours at a microscope looking at probe marks, big probe marks, bad probe marks, post-mortems, probe card damage, you name it, I was involved with. Okay, this is another form of the another form of the 196. It was a CA, it was an SA, this was a CF, this is already a different, up until now we've looked at dies which were on P648, this is on P650. Process 650. Today's process is P1274, so we're looking at 25 processes back. It's not exactly true because Intel doesn't go chronologically on the processes, but 6-inch 650 and 1274. Okay, this is a JA processor. This is an HT processor. Okay. Okay. We're now looking at another. This is a a news site from 2006. Intel crashes its ancient chips. These were the chips that I made. Okay. So I have a picture here of an Intel DX2. Okay. Intel DX2. It reminds me once again of a story. The story is not around Intel DX2, it's around Intel DX4. Around Intel DX4. Okay. So I'm now going to explain something around testing hardware. We understood up until now. I explained the type of work I did with production. This story is going to be around Intel DX4. Okay. Now the Intel DX4 had a probe card, like all other devices. It had a probe card, and this probe card had, if I remember correctly, larger capacitors on it than usual. And I think the capacitors were even, if I remember correctly, tantalum capacitors. Okay. Tantalum capacitors. Okay. So now, if I move away from die-based, I'm now going to speak about tester hardware. Okay, now in the tester, you have got two ways of powering up a device. You can power up the device via DDPS, which would mean a 4 amp power supply, which would mean I'm powering up my chip via a 4 amp power supply. And you had a second way of powering up a chip, which would have something like a 5 to 10 milliamp range, which you'd, instead of using your power supply pins, which would be on the crescent boards outside, you would be using one of the logic pins connected to the power supply rail to get a better resolution of measuring your current. Okay, so we're talking about the DX4. So I'm now going to speak about DX4 and IPD, which would mean power supply, low voltage power, IPD, power down current. So what would happen is your device would be powered via a power supply from the crescent boards around the head, and it would run a pattern. The pattern would put the chip into a low power mode. At this point in time, when the chip was in low power mode, the pin, one of the logic pins, would be connected to the VCC rail. A relay, and I'm talking about a physical relay, which was software controlled, would be closed. The voltage power supply, which is a VI, which is not a DDPS, would create voltage and your original power supply that was used to power up the chip, the big power supply, would disconnect. And you would then measure your current on a high resolution using your VI or your parametric tester instead of using your power supply as a tester. Okay, that was background. What happened? If you had a calibration error between your power supply and it was powering up the chip and your VI power supply, you would have some type of higher or lower voltage as you switched power supplies. And what would happen was you would get readings of your 486 DX4 creating voltages. You get current flow apparently from the chip because there wasn't enough time left to, there wasn't enough time delay for the device to measure the power supply. Because when you are measuring, you are not measuring the current IPD of the DX4, you are measuring the current of the left on the capacitors between the voltage changed. Okay, so how did I get around this? I got around this by increasing the time delay between disconnecting the original power supply and the measure. Okay, this is something that was related to 486 DX4. So this is a story. This is what I did for many years. Okay, i960 DX4. So to go back, what was my tasks at Fab 8? Fab 8, I used to be the person to I would run production. If there were yield problems between testers, I was the person they'd blame. They wouldn't come and say to me, we have a problem. They'd come and say to me, your tester isn't working properly. I was never the owner of the tester, but I was always the person to blame for when things went bad. Okay. Be that as it may, I was the person to blame. 13 years at Intel, I never got once above expectations. But every time there was a fault, I was the person they'd call. It just goes to show the culture. When what you do means, when what work you actually do means absolutely nothing. Okay, so we spoke about production. Very often it would be, they'd scream, Aria, your tester is coming, your tester's throwing out bad dies, bin 15, which opens, and I'd come and I'd look down the microscope and I'd see that there's dirt on the pins, and I'd take out my brush remove the dirt, and continue running. Okay, this is what I did for 13 years. Production, as well as there were 16 testers. When they decided this tester couldn't run a particular product because it had a problem with some tester hardware, I was the person that had to go and sort it out. Okay. That's basically what I did for 13 years. Okay. I have a story about 8051, which is very much along the lines of this story. This is a story about a test program. The 8051 story is more story about automation. Thank you for your time.